Hi, welcome everyone. This is the session before lunch. We only have one session in this room, so sorry I was a bit disorganized. But welcome Joe Manning, co-founder at Secret Labs. He will be talking about symbolic analyzers. Thank you.
Hi everyone. There we go. How are we doing, everyone? Excited for lunch? I am. I'm very excited for lunch. And also, I'm here to be excited about talking about symbolic analyzers and how we can use them to find bugs in our code. So what I'm going to do today is I'm going to show you how to write a program that can find bugs in other programs. That's the whole thing. So buckle up for a half an hour of that kind of content if that's what you're into. A bit about me, I'm a game developer. I work at a studio called Secret Lab, 50% of it. We're best known for a game that we helped on called Night in the Woods. We also have written a number of books for a company that you may have heard of called O'Reilly Media. They do something to do with animals. I also work on a thing called Yarn Spinner. Yarn Spinner is a language for writing interactive dialogue in video games. And in fact, that was the thing that kicked off this whole idea that ended up becoming this whole presentation. So, I mentioned a game that we helped on called Night in the Woods. Night in the Woods is a game with a lot of dialogue. It has a lot of player choice. There's about 25,000 lines of dialogue in the game. The way that the dialogue is represented is in a language called Yarn, which is part of the Yarn Spinner system that I mentioned earlier. And there are, as I say, a lot of lines. We need to verify that all of the lines of dialogue in this game can be reached because each one of those gets translated and gets presented to the player. And also, this game didn't have it, but you can very easily extrapolate this into games where there's voice acting. How many actors are you paying for, and how many lines are being wasted by never being able to be reached? We represent it in a node-based configuration. In fact, this is just a tiny, tiny snippet of some of the game. This is much more complicated. That's also a tiny, tiny snippet of the game, and you can see how complex the branching model becomes for even simple dialogue in games. So, we want to answer this question. Is every single part of this program reachable? Or, to put it in a more formal way, for any given part of the program, is there a way to prove that at least one input exists that reaches that part of the program? So can we prove that inputs exist that are capable of reaching any part? This is computable, and this is the focus of our talk today. So I'm going to be talking about how symbolic execution works, which is a technique for analyzing source code without actually having to run the source code. I'm going to talk to you about how you can use a theorem prover to assist in this, and also how to pretend to run code without actually doing it, which can save you a lot of heartache. So, let's get started. What is static analysis? Static analysis is when a program looks at your code and figures stuff out about it. It analyzes it without actually running it. So static, if you imagine it as not actually moving, nothing's actually happening inside the computer apart from the code existing in memory. Now, a compiler does this all the time. Every single warning that you see emitted from a compiler is the result of some form of static analysis. Symbolic execution is running the program without having any knowledge of what the inputs to that program are. Now, running a program normally requires, in order to execute a program at all, you need to have inputs in order for it to function. Symbolic execution means you don't have to have that at all. Now, if you don't know the inputs to your program, then you cannot know the concrete value of any of your variables. But what you can know is some facts about what those variables are allowed to be. So you can't know the actual value, but you can know stuff about those values. So here's my challenge for the first part of today. Prove that the very last line of code here can run. You're not allowed to run the code. So how can we do that? Well, we'd say, well, we don't know what the input is here. So we're not allowed to actually run the code, input how many pies. But we do know, OK, first line, pie price is 3.14. That seems appropriate for a piece of pie. Now, we hit our first problem. Number of pies is the result of taking user input. But we're not allowed to actually capture that user input. So what do we say? What's being stored inside numpys? Well, it's, don't know. Can't know it. So instead, we represent it with a symbolic value. We say there is a value, it exists, I know nothing about it apart from the fact that it does exist. We'll call that pi. Pi owing is pi price times num pi's. We can't know the concrete value of this either because it depends upon a symbolic value. So we say, therefore, pi owing is pi times pi. So if we have reached the last line, in order to reach this, the only way for that to be the case is if pi owing is greater than 10. Therefore, this fact about the world must be true if we're on this last line. Pi owing greater than 10 is true. All right, so that seems fairly straightforward. But now how do we represent this in code? How do we write a program that can reason about these symbolic values? Because the object pi needs to represent not just a placeholder for a value, but also a placeholder for a value that can be operated on like actual concrete numbers. It has to have the same operations as any other number, plus, multiply, all the things that a number can do. This placeholder has to be able to do as well. So we now have this problem. How do we think and reason about these placeholders in a way that's useful? To do that, we can use a theorem prover. Z3 is a library written by Microsoft and released under the MIT license. It is fantastic. It is available on pip, Z3-prover. It's actually not written in Python. It's actually a C++ library, but there are bindings for most languages ever, and the Python one is pretty good. So what Z3 is capable of doing is proving logical, among many other things, it can prove logical problems. So I see people taking photos. I'll just leave that up for a second. No, brilliant. OK, so here's a simple example of the kind of problem that Z3 can solve. Here's simple logical syllogism. If it is raining, I'm wearing a raincoat. It is raining. Therefore, yeah, that's right. Well done, you logician, you. So we can represent this in code in Python like this. We import from Z3. And we say there are two variables that exist. One's called raining, one's called raincoat. We create a fact about the world. If it is raining, I'm wearing a raincoat. If raining is true, it implies that raincoat is true. We can then ask Z3 to solve this set of equations. We can say solve given the fact if raining then raincoat and also the fact raining. And it will produce raining is true because you've told me that it's true, but also I've inferred that raincoat is also true, following the prepositions that we've set up. Okay, so that's the groundwork for using symbolic representations and having Z3 solve this logical problem for you. So now we have all the tools we need to answer this extremely important problem if we assume that we have reached the very last line in which we print you're over the pi budget. How many pies have we ordered? We can't know the single correct answer, but we can know a correct answer, thereby proving that it is reachable. So let's take our code and rearrange it a little bit. So on the left-hand side here, I've got the original Python code. And on the right-hand side, I'm going to start writing out the set of equations that we would feed into Z3 that would allow us to derive a value for number of pies. Okay? Now again, not the correct answer, just a correct answer for number of pies. So let's start. We say pi price equals 3.14. So we'll declare a variable, a real number called pi price, and we'll declare to the S3 solver that it is true that pi price is equal to 3.14. So we've declared this. Then number of pies is the result of user input. We don't know it. We have to represent it as a symbolic value. So we say num pies is integer value num pies. We don't assert any facts about its actual value, just that a variable exists. Pi owing is declared similarly. We declare that this becomes symbolic because it depends upon a symbolic value. And then here, if we have reached this point, then we add one more constraint, pi's owing is greater than 10. That's the condition necessary to reach that line. We can then tell Z3 to solve the accumulated set of equations we provided, and it will return the value sat. That's short for satisfiable, which means that all of the formulae that you've provided to it can be true at the same time. If we had provided, for example, equations that are not mutually compatible, if I said, for example, a is equal to 1 and a is equal to 2, That can't be true at the same time, and therefore such a set of equations would be unsatisfiable. So we say S3.solve and it says sat, satisfiable. And then we can say, all right, smarty pants, then what is the value of numpys? And it will produce a valid value for the variable numpys given the set of constraints you provided. In this case, 4. That is a valid value that can be true if pi owing is greater than 10 and pi owing is number of pi's times pi price, and pi price is 2.14. It's figured the whole thing out. So this is cool as hell. So that's great. We've solved a bakery problem, but we haven't solved a real bug yet. Let's take this approach, which we use to solve a bug by hand, and then generalize it into an automatic process. How can we solve the code reachability problem, which is only one class of bugs, but it's still a fairly interesting bug to explore. So we're going to focus on this today. So I have one more challenge for everyone here. Spot the bug. You may be able to guess based entirely on what I've just said so far leading up to this. The line print hello will never run under any circumstances. There is no way for that line to ever be reached, regardless of the value of a that is passed in. Okay? I'll let you stare at it for a second and confirm for yourself. But how do we prove that? I know it. I wrote the slides. You know it because you're very, very intelligent. But how does the computer know it? So here's how we do it. We find every possible path that can be taken through this program. We run symbolic execution on the path, which generates a set of constraints that apply to each path. We can then detect if, for any path, that path is unsatisfiable and remove it. And if no paths remain that reach a line of code, that line of code, therefore, is impossible to reach under any circumstances. So we have created a system for generating proofs that it is unreachable. OK, let's take this one step at a time. How do we find every single possible path in a program? Well, there's a slide. We can do code graph analysis. So who here, raise your hand if you're aware of the fact that Python is a bytecode interpreted language. Yeah, some of you, yeah, about 2/3 of you. Cool. Most compilers, in fact, produce bytecode, not because bytecode is cool and fashionable, although I'm sure that's part of it, but also because bytecode is very, very easy to analyze. It makes things much, much simpler. It makes it very long, but that's fine because we aren't the ones writing that anymore. We can then create a graph from that bytecode and then analyze the graph, which is real cool. So CPython compiles to bytecode, and we can actually disassemble any piece of compiled Python. Like you can take a function and say, now give me the bytecode for that function. This is using the dis module, which is part of the standard library. So if you say dis and then pass in a function, well, you get this for our test case here. So here's on the left-hand side the original code, and on the right-hand side, that's Python bytecode. Now what's really cool about Python bytecode is it doesn't have any registers. It's entirely stack-based. That is, all the operations that take place are done by pushing values onto a stack, and then functions get called which pop values off the stack, perform some work, and push the result back onto the stack. And that's a very, very simple model to think about. You don't have to worry about register allocation. You don't have to worry about like where stuff exists in memory. You can just think in terms of a stack. It's slightly more complicated when you start thinking about, for example, closures and frames, but for the purposes of this talk today, it's good enough. So we can see, for example, line by line, how each line maps to the actual behavior being executed on the Python virtual machine. So when we say x is equal to 0, what we're saying is push the number 0 onto the stack and then store it into a variable called x. And then in this if statement, where we're checking if a greater than 0 and a less than 5, we are pushing the variable a onto the stack, we're pushing the variable the constant 0 onto the stack, and then we run the comparison greater than. And then if that turns out to be false, we jump to instruction 24. That's about halfway down the screen there. And then a very similar thing happens there. So we're just doing very, very simple operations that are much easier for our kind of analysis to reason about. So storage works in a very similar way as well, which we've seen. OK, so now we have a linear list of instructions which are simpler tasks. How do we find the flow of behavior from top to bottom? What possible paths could be taken? Now, you could stare at that for half an hour like I did, or you can do what compilers have been doing for the last 40 years or longer, and that is basic block analysis. A basic block is a run of instructions that is guaranteed to only ever be entered at the top and only ever exits at the very bottom of the run. And that makes analysis so much simpler because you never have to worry about leaving control flow in the middle of a run of instructions. You start saying, okay, now I'm dealing with indivisible blocks of instructions that I know you'll never enter into anywhere apart from the top, and you'll never leave from anywhere except the bottom. So to find a basic block given a set of instructions, the number of rules involved is actually very simple, very minimal. An instruction is the start of a block if it is the first instruction in the program, if it's the target of a jump from somewhere else, if it's the instruction after a conditional jump, or it's the instruction after a stop instruction. All other instructions can then be grouped up. So given our list of instructions in Python bytecode, we can say, well, here's the first one, and we know that it's the first one because it starts at instruction 0 and then ends at a jump. And the next one, and that jumps down to instruction 24. And the second one, because it is a new block because it is the instruction following a conditional jump, going to the same point. Then the same one for the same reason, instruction following conditional jump. And so we can use that to build up all of the blocks that exist in the program. Now we know what the indivisible building blocks of our program look like. And we can start thinking about how each block moves from one to the next. So blocks have predecessors. These are the blocks that can lead to a block. Blocks can also have successors. These are the blocks that it can go to. Blocks that end in an unconditional jump, that is, it's like a go-to, which is still very popular in assembly, have one successor, which is the target of their go-to. Blocks that end in a conditional jump have two, which makes a bit of sense. You either have the true path or the false path. Blocks end in stop have none, because they stop the program. And any other block has one successor, which is the block that the following instruction belongs to. So to visualize this a little bit, here's our instructions divided up into blocks, and we rearrange it, and this is the control flow graph of that function. Now we know what possible paths could be taken. Given any input, you'll start at the left-hand side of the graph, and you'll end at the right-hand side. And depending on the conditions, depending on certain values on the stack, we'll either take on these nodes here, the false path or the true path. Now, there's only a certain number of paths that go to the print hello containing block. That's the second from the right-hand side, where it says load global print, load const hello. So not that many paths go through there. So let's take a look at one of the paths that we can go to and see if we can prove that it is either a valid path or not. So we start here. And so here's the instructions involved in this first block. Now we can clearly see that what is stored in X, all paths go through this block, and in the very first two instructions, we store the value 0 into X. But when we get to the next instruction, we say load A. We don't know what that is. There's no way to know it. So what we have to do is we have to declare that this is a symbolic value. Now I'm going to call it cat, just because I like cats. So we can now move on to the next one. If we came from the true path, because that's the yellow highlighted path we're following, now we know this is the only way to get to this blue block is if A is greater than 0. So because A contains the value cat, that means that cat is also greater than 0. So we've gained more information about the possible values of the variable A in all circumstances. It is impossible to be at this block and have the variable A not meet this equation. So we follow another test, and we end up here, which sets X to 1, and also gives us further info about the value of cat. We know it's greater than 0, and now also less than 5. All paths end up going in through here, and we'll shift across. And then we have another set of tests. We are checking to see, okay, if we're taking the true path, that means that x must be equal to 1. We have already defined that, so to save space, I won't add it again. So taking the true path, we'll move on to the next one. But also, because, in the previous block we said that the variable b is equal to a plus 1. Therefore, we can infer that b is less than 6 and b is greater than 1. Finally, we hit this test, which is the last check we have to do. If we take the true path here, then we're golden. We can get to our print statement. Okay, so what constraints must exist if we are here? Oops. This is only reachable on this path if b is less than 6 and also greater than 6 at the same time. So, therefore, this path is unsatisfiable. We cannot have all of these equations be true at the same time, and therefore, this whole path is impossible. And by running this on every other possible path that can reach that load global print load const hello call function, all of these are impossible. So we have automatically proved that there is actually no path that reaches this print statement, and therefore the whole thing is impossible. So how can we use Z3 to derive those constraints? I did it again by hand. We can figure this out. We take the collection of all basic blocks. We identify all the blocks that are entry blocks, that is, they have no predecessor, and all the exit blocks, they have no successor. And we find the paths between each pair. Next up, we then take each path and execute the instructions as normal, but with two main exceptions. When we say we set a variable, we now are not saying, oh, store the value in memory. Instead, we're saying we're asserting that the variable is equal to a certain value, and that value might be derived from previous operations. Secondly, when you hit a conditional jump, you already know what direction you're taking. So if you're taking the false path, you assert that the condition is false, and if you're taking the true path, you assert the condition is true. And all of these help to create the constraints for the path. So just as an aside, this is slightly more challenging if you want your variables to be able to change, which is quite popular in programs. So you've seen code that looks like this. X is 1, but now x is 2. Y is equal to x plus 1. So if we were to represent that in a set of formulae, it would look like that. So x is equal to 1, but also equal to 2. And Z3 goes, nah, mate. So that's unsatisfiable. Instead, what you're required to do is record history of variables over time. So rather than there just being two variables, x and y, now there's x version 1, x version 2, and y version 1. And this is satisfiable. x1 is 1, x2 is 2, y1 is x2 plus 1. That's satisfiable. That is a thing that the Z3 solver can reason about and say, yes, it is satisfiable, and also here are some possible values for all of these variables. This is actually the technique applied in LLVM. LLVM is the compiler infrastructure that supports C and C++ and Swift and Rust and many, many other languages. And you'll notice how all of the assignments, that's the percentage sign and then a digit at the end of it, those are all registers in the low-level virtual machine, are only ever being assigned to once. This is a thing called single static assignment. In single static assignment, you are only ever allowed to set a variable once. If you want to change it, you've got to have a new variable. And that actually makes it way, way easier to think about using, for example, theorem provers. So the code for setting the contents of memory changes from the simple, if memory is dictionary, then you'd say that up top here, self.memory variable name equals value. We don't do that anymore. We say there is a new symbol. It is basically we're versioning our variables. We assert a new value being equal to that new symbol, and then we say that the memory now contains a symbol rather than the value. And the conditional jumps look very similarly. We say if we are doing a pop jump if false, which is basically the conditional branch in Python bytecode, then we say, well, if the thing that we're looking at on the stack is actually an equation rather than a concrete constant value, then if we know we're taking the true path, we assert that that equation is true. Otherwise, we assert it's false. And so now we're continuing to accumulate all the assertions required to define this path. Operations are actually largely the same because the add operation, among most other things, is defined on both numbers and on Z3 expressions. So most of the virtual machine actually remains the same. So you can say, oh, add is defined as stack 1 plus stack 2. That's still the same code. So now we can detect the impossible paths. We have all the constraints. We feed them into Z3, ask if the constraints are satisfiable, true all possible to be true at the same time. And if it's unsatisfiable, that means that the set of constraints that defines that path is impossible, and therefore the path is impossible. Repeat for every path. So there are a few ways that you can use this. One popular way of using this is generating input cases for code coverage. Because you can generate a valid input for every valid path. Keep those in a file somewhere, and then when it comes time to run your unit tests, you can provide the same inputs again, and you'll run all of the possible valid paths where feasible. You can also use it to prove that code doesn't get reached. So ever written code that goes, we'll never get here, and then you got there? Yeah. Well, using this, you can turn this whole thing on its head. You can say it's a failure if the path is actually valid. We never want any paths that reach this here. I want to catch those with if statements or exception handling. So you can use that to prove that your assertion failures will never happen, that they're adequately taken care of. You can use this to also get a more clear picture of your code as well. You can add invariants that define information about the world in which your program runs that the code does not necessarily define. So for example, you know that the temperature reading that comes out of your temperature sensor will never be below 0 Kelvin. But there is a universe in which that could exist, at least insofar as your code thinks. So you can define that ahead of time. You can say, my temperature variable will never be less than 0. And therefore, you can use that to define you can use it to infer a broader set of constraints and find more error conditions. Now, this is not a panacea. There is no silver bullet. It has some problems. One, path explosions. If I've said compute every possible path, well, what if there's an infinite number of paths? What if there's an infinite loop in there? You've just broken your theorem prover. What if you have multiple variables all reference the same memory, aliasing? That can be challenging as well because it's very, very difficult to automatically detect that. If you're dealing with arrays, is an array a value, or are the values inside the array separate values? How do you represent that in your formulae? A thing to think about. And also, this is more challenging in any situation where we have dynamic types. Now, Python is one of those. So a solution to that is to add, for example, type hints. That helps your static analyzers reason about your values. So for further reading, I'm on Twitter. I'm disclosed in my studio is the Secret Lab. If you're interested, go and take a look at Yarnspin as well. I'm pretty proud of it. More information about will be on this on the site secretlab.institute later on, and also you can get Z3 on GitHub there. Also, strongly recommend Alison Kupta's book 500 Lines or Less because she and her co-authors put together an entire implementation of the Python bytecode interpreter in about 500 lines of Python, which is real cool. So a lot of inspiration for this talk came from that. And thank you very much.
Thank you very much. I think we have like 1 minute.
Right.
Does anyone have one question?
Thanks, that's great. I have a question maybe in a kind of more complicated sense. Imagine your input was like a dictionary. Is there a way to use this interpreter to go back and tell you, for example, like for this path to be reached, your dictionary must have this, or it's almost like backwards engineering?
You're talking about you want to be able to test to see what, so any test that results in a Boolean condition, which is any test, can be represented in the same way. So the answer to your question is yes, you could, but it would require more code.
Okay.
Yeah, so like absolutely that this technique can be applied to that. You also mentioned like going backwards in time. Yes, you can also do that. In fact, a lot of hybrid symbolic executors they'll actually save the state of all the symbolic values to file, and then evaluate paths that branch off that. And if they hit too many failures, give up, go back to that checkpoint. So you can kind of go back in time a little bit using that technique. So hopefully that helps.
Thank you very much for your talk.
Thank you.